let's start the main lecture material then. We're starting today with Chapter 2 of the book, and the topic is object orientation. It's assumed that you have some understanding of object orientation because you will have taken Java before taking this course or reading this book. Okay? If you don't know Java, then you're on your own in terms you have to go and learn Java in a hurry on your own. Okay? I will be reviewing some key concepts. Some of the deeper concepts like polymorphism and interfaces and things like that will be covered, and we will be getting into issues of client-server and threads and things like that, and sockets in some detail in this course. But you should know the basics of Java and how to create basic classes and constructors and things like that. So what we're going to do now is to start by taking a look at object-oriented principles in general. And this will continue over into next lecture because, in fact, there's quite a lot of somewhat deep concepts that we have to get our minds around here. Let's take a step back in history first. We're going to first think about what came before object orientation, which was basically what's called the procedural paradigm. In the early days of software development, before we even had the word software engineering, people thought in terms primarily of procedures. They might have also been called subroutines or functions. Later on, methods. There's a number of different words, but they're all basically the same thing. They're basically procedures. You call them, they start executing, at some point they return. And these get nested into hierarchies. You have main programs, subprograms, sub-subprograms, etc. Okay, so software was organized around these, and people thought fundamentally in terms of the procedural abstraction. You know, you call a procedure, and what's inside you don't care so much about once it's programmed, you just care about the result that comes out. So you're abstracting the details of the innards of that procedure away and thinking about its function, what it does. That's the kind of abstraction that we were used to until object orientation came of age in the late 80s, early 90s. After a while, people began to realize that procedures on their own were not powerful enough abstractions. We were dealing with data that became more and more complex. Procedures work fine when you're passing in little parameters like numbers, integers, floating point values, maybe some strings and characters. Fine. A lot of the early computation was all scientific and engineering in nature, calculating things, and you're spitting out numeric results. Maybe that you spit out arrays of numeric results or print the results out. Okay, so the data was relatively simple, even though the calculations might have been quite complex. But at some point in time, the data became very complex. In the early days, the first thing people did was decide that they were going to create the concept of what's called a record. In fact, this came about in a big way when the COBOL language was developed, which is still actually in quite wide use today. Records are units which are broken down into fields containing different pieces of data. So you might have a record describing a student, which has their name, their student number, their date of birth, and a few other things about the student. So these are data abstractions, either records or structures they're typically called, and they were used in the context of the procedural paradigm. But the data continued to get more and more complex, and at some point in time, people realized that they were operating on these data abstractions from all kinds of places in the program. So you began to get a spaghetti of bits and pieces modifying data and accessing data all over the place. Big mess. What you started off with was a nice hierarchy of main programs, subprograms, sub-subprograms, easy to understand, became a mess of accesses to data all over the place. So what it was decided to do was to switch and organize programs around the data. And that was the genesis of the concept of the class. Organized programs where you have classes, each representing a kind of data, and your procedures are put in the classes. Instead of having the other way around, where you have data modified by procedures, you now have procedures in classes. And that helps to simplify the overall structure of systems, allows you to make more complex systems that do more, but are still maintainable and still understandable. The object-oriented paradigm actually came into being. The early genesis of it was in the 60s with the similar language. Smalltalk was the dominant OO language through the 80s. Wasn't until C++ hit the streets in the late 80s and Java in the early to mid-90s that we really got into the dominant object-oriented paradigm in the world of new development. However, remember, a lot of the software that's out there is old software, and so a high percentage of all development is still fundamentally procedure-based, using older languages. So if you go out there working on maintenance or evolution of custom software, still use a lot of procedural paradigm. So we can define the OO paradigm as an approach to the solution of problems in which all computations are performed in the context of objects. Okay? These objects are instances of our classes. Chunks of data. We'll define those in a minute. In fact, it's right here. All objects are instances of classes. Okay? They're data abstractions. So the object is a more sophisticated form of a struct or a record. And the classes themselves contain procedural abstractions that operate on the objects. And we can think about the running program as a collection of objects, all doing their own thing. Okay? If we have threads in Java, then a lot of things can be going on in parallel with each other. This slide 4 gives us a graphical view of the two paradigms. On the left, we see the classic way of looking at the hierarchy, the call hierarchy with the main program, subprograms, sub-subprograms. Very small example, of course. Classically, this goes down deeper and deeper and deeper. On the right, we see the classic class diagram. In this case, it's a small inheritance hierarchy. This is the first tidbit of UML that you've seen, with much, much more to come. We have a class called account. It has some operations, credit and debit. The triangle means the account is a generalization. It's a superclass. We have two subclasses, checking account, savings account, which have their own specialized methods down below. Okay, so that's a classic view of the object-oriented paradigm. This is how we organize object-oriented systems. Fundamentally, there are other ways of thinking about them too, but this is the fundamental way versus what's on the left, which is the fundamental procedural way of thinking. Any questions before we go on? Okay. Let's define a few terms then. We're going to talk about objects versus variables versus classes. Some words and terms that are related to each other and can sometimes cause confusion and misunderstanding. It's important that most of you probably already understand these reasonably well, but there will be some misunderstandings in some people, and I have to make sure that those misunderstandings are completely cleared up. First of all, the object is a chunk of structured data in a running software system. Could be in random access memory, could be on a hard drive in a database somewhere. Okay, there's a number of different physical places where the object could be, but we think of it as a chunk of data. That's the way to think of an object. Okay, it represents something in the real world. Okay, it has a number of properties. We're going to talk about properties in a more specific way later on in terms of attributes and associations and so on. But in general, we can call them properties. Okay, that represent its state. So a student has a particular name, a particular student number, a particular set of courses they're registered in, etc. And an object has a behavior that defines how it acts and reacts. These are the methods that are contained in its class that apply to it. Okay, so an object can only behave in certain kinds of ways depending on what its class is. And often there's some sort of idea that these objects simulate the behavior of things in the real world. So an object in a university registration system that is a student, a particular student representing you, is in some sense representing the real you. It's an object in the program representing the real live object in the real world. Okay, I think these concepts are relatively straightforward. No problems for most of you, probably. If there are, just raise your hands and I'll answer them. We can draw a diagram of a few objects if we want. Here is a way of representing objects in UML. You show them in boxes. You have the name of the object, colon. You can follow it optionally by the name of the class. We'll see that official definition later on. In this case, I'm not showing class names at all, just object names. One of the key things is you've got to underline the name. If you don't underline the name, then it's confused with the class. So the underline and the colon indicate object as opposed to class. Another thing we see is that each of these has data, actual real data. So the date of birth is, for Jane, is 1955-02-02. Okay? And the address is 99 UML Street, and the position is manager. The actual data is filled in. Okay? If we were showing a class, we would just say that we have a class called person who has a date of birth, address, and position, and there could be many instances defined from that class. If we're showing an object, we show the actual data, the name of the person, and the other data directly. Now, it turns out that we're not going to actually draw objects very often in the early stages of this course. They'll show up a bit later on. Most of the time, we'll be working with classes in the early going. But you have to imagine that, yes, you have classes we're working with, but they generate objects when the program runs. Questions? Okay, slide 7 then. What is a class? Okay, a number of ways of thinking of a class. It's a unit of abstraction in an object-oriented program. Fine. So it's an object in some sense, except an object is at runtime, a class is at design and compile programming time. Represents similar objects. We call these objects its instances. The word instance and the word object can be used interchangeably in many contexts. Okay, if you look at the book, I describe that in a bit more detail. But if I talk about an instance, I mean an object. And, probably most importantly, a class is a kind of software module. Okay? That's what we've got to think about a class as being. It's something which we design and program. It describes the structure of instances that will be created at runtime, and it contains the methods that will be executed on those objects at runtime. Okay, questions? So, objects versus classes. Now, it turns out that, although most of you probably say, well, I understand that, that's clear enough. When it comes to actually doing object-oriented analysis, people fall over themselves. They make mistakes that maybe even surprise them sometimes, making a mistake about what's an object and what's a class. So on this slide 8, we have a few examples of things that words that you might see, or terms that you might see in a requirements document, for example. Now imagine that we're dealing with a requirements document for a film studio that makes movies, and we're implementing their information system. So in this requirements document, one of the things that you see, it talks about films. And your first thought is, well, are these films classes? Or are they objects? Is it talking about a specific object, or is it talking about a general class? And what you have to do is ask yourself, well, is it talking about something which is going to have instances? Or not? In this case, yes. Clearly, there will be many films. And each of those films is going to have instances which are individual films, like Sound of Music, Star Wars, etc., etc. Okay, so film is a class that has instances. What about reel of film? Now, this is where people start to make mistakes. They see film, they see reel of film. They say, oh, okay, great. Well, reel of film must be an instance of film. First response for some people, very wrong. Okay? Reel of film is also a class. It has instances of its own, which are totally unrelated in some sense to the film. The film is a class of abstract things, films. The reel of film is a class of things which are physical chunks of hardware, that, well, reels of film that you send out to movie cinemas to play. Okay, and each one might have a stamped serial number on the side and a label saying what it is of. Typically, you know, when you send the Harry Potter film to a cinema, it's going to have 4 or 5 reels, depending on how long it is. Okay, each of these reels is separately identified, and there's a separate object. Okay, so a reel of film is a class whose instances are physical reels. What about film reel with serial number SW19876? That is clearly an instance, because now we're saying this is representing one individual thing. We're giving it an identification number. It's a chunk. It's going to be represented in our system as a chunk of data. Okay? Instance of reel of film. In fact, instance of the class above. Science fiction. What's that? Is that a class? Is that an instance? Yeah. Again, you might grapple with that a little bit. Maybe it's neither. It could be neither. You could design a system that just didn't store, you know, the type of film. But we're going to say, well, science fiction is going to be an instance of a class called genre. Okay? Other instances might be horror or comedy or whatever. Science fiction is just one of many different instances that it can be used to tag different films. Okay? Science fiction film, on the other hand, is clearly not describing an instance of genre, but is describing a class or subclass of film, okay, whose instances include Star Wars, The Empire Strikes Back, and many other science fiction films. And there would be maybe another subclass of film called horror film, okay, which would have its own instances. So science fiction as a genre would be an instance if you decided to have it in the system, but science fiction film is a class which has instances. So one of the typical mistakes somebody might make is say, okay, we have a class called film, and we're going to have a subclass of that called science fiction. Okay? When what you really should do is call it science fiction film, just to identify that it really is a kind of film. And finally, showing of Star Wars in the Phoenix Cinema at 7 p.m. is an instance. It's got full of data. It's got a precise time, a precise place, precise film. It's clearly an instance of something. And in this case, the class might be something called showing of film. Okay, so you're going to have to, as you start getting into object-oriented design and analysis, think in some detail about what the class is. Okay, you have to have a reasonable understanding of what the class is and what the instance is, and make sure that you get them right. Is it a class? Is it an instance? Before we leave the concept of classes, I want to talk a little bit about some problems people have in appropriately choosing names for classes. Okay? First of all, if you have a class, if you define a class, give it a capital letter. Classes should be named using a capital letter. So, capital B for bank account. Whoops, there. Not lowercase b. If you show a lowercase b, people will read your program and think it's a variable. You want them to understand it's a class, you use a capital B. This is a convention that has been in place since the days of Smalltalk, and it's pretty well standard through OO. Sometimes it gets violated, but in general, you should stick to the capital letter. Secondly, use singular nouns. Okay? Don't name things in the plural. If I go back a slide and I see film, I don't call it films. I don't call the earlier one accounts in the plural. I call it account in the singular. Okay, that's a convention. If you don't follow that convention, you're going to end up confusing people, because people look and see a singular name and think it's going to have many instances, say, of account. If I see accounts in the plural, then they're going to think that the instances of that are a set of accounts. Okay? So if the class name is singular, people think an instance is one of them. If the class name is plural, people think the instances are a set of these things. You don't want that. Generally speaking, you want one object represents one thing. So a few of you might make this mistake sometimes. A few of you might make this mistake. The next two mistakes are slightly more common, and you have to guard against them when you're doing your work in this course and in the industry. First one is choosing the right level of generality for your class names. So let's say that I was designing a system that was supposed to be running the property tax environment in the province of Ontario. Okay? The province of Ontario has many cities, towns, and villages. Collectively, these are called municipalities. There's a tendency for people to, when they create forms, to have a box that says city. Okay? I'm sure many of you have filled in forms where you're told, fill in the city you live in. But not everybody lives in a city. So when you design classes that are supposed to represent things that may not be cities, maybe towns, maybe villages, you don't call them cities, you call them municipalities. Use the term that is at the right level of generality to represent all of the instances. And finally, and this problem is a problem that is very widespread and very subtle, and probably at least half of you will make some mistakes of this fourth kind. Make sure that the word you use for your class has only one meaning. Let's say that I was designing a system for the bus company OC Transpo in Ottawa, and I decided to create a class called bus to represent these big things which have wheels and seats, and people get on and off, and it's got a number on the side that, you know, 9573 represents the 75th bus bought in 1995, and it's painted red with a Canadian maple leaf on it and stuff like that, right? It's a bus, clear enough. And in my OC Transpo system, I'm clearly going to be wanting to represent information about my buses, what's their maintenance schedule, you know, when were they made, etc., etc., etc. But that's not the only meaning of the word bus. Can anybody tell me, in this type of system, some other meanings in which, in ordinary English, one would use the word bus? Different meanings where the same word tends to be applied. Yeah?
Topologies.
Say again?
Topologies.
Topologies?
Yeah, network topology. What's topology?
Okay, no. In the context of a system for transportation, for OC Transpo. You're absolutely right that the word bus has meanings in electronics as well, but in this particular system. Anybody got any thoughts? Come on, somebody can get it. The other class, somebody got it. You can get it too. No? Yeah?
Routes.
Exactly. Exactly. So, imagine the situation where you say, bus 16, I'm going to catch bus 16 to get to your place. Or every day I catch bus 16 to get to your place. You use the word bus in ordinary English when you really mean bus route or bus route. So that is exactly a context where people will typically put down bus when they mean bus route. And notice that the properties of that are different. The properties of a bus route are, you know, the bus stops it goes to, and the number of the route. Whereas the properties of the bus, the other kind of bus, we should call it bus vehicle. You know, the hardware is the bus vehicle, this is the bus route. We should use the word vehicle and the word route to distinguish among different possible meanings, possible interpretations of that word. Don't use the word bus for bus vehicle because it could be interpreted differently if you mean the route. There is yet another possible English language usage where people will informally say bus in the same application domain. Anybody think of what that might be? Yeah?
To travel, take the verb.
Okay. He said the verb to travel. You know, I'm going to be bussed from here to there tomorrow. Yeah, okay. That's a good observation. It wasn't what I was looking for. Because one of the things that we will see is that basically what we want to do is we want to name our classes after nouns, not verbs. But good observation, good try. Any other thoughts about where we might use this word bus? It's a bit subtle, so I don't expect you necessarily to get it, but it's something that you have to be on the lookout for. Okay, let's say that I said, I'm going to catch the 9:30 bus to Montreal tomorrow. Is that a vehicle? No, because it could be any old vehicle that shows up at 9:30. Is it a route or route? No, it's not, because, hey, there's many different buses running over that same route at different times of the day. It is a run of the bus route. Okay? In English, I can use the word bus to talk about a specific run that picks me up at a specific time on a specific route. So, I have bus vehicle, bus route, bus run. Separate things. The run has the start time and the time at which it gets to each individual stop, whereas the route just has the sequence of stops. Different things, subtly different, but in the object-oriented context, absolutely critical. A, that you have those three classes if your system is going to be managing that kind of information, and that you carefully distinguish them and you don't confuse people by mixing them up or using the same word for the same thing. Believe it or not, there are plenty of times where people will mix those, especially those last two. They'll design an OO system where they mix the route and the run together and try and hack together software that will work with those together. And it is very complex. It is way more complex than it needs to be, and it doesn't really represent the real world. So what you have to do is figure out classes that represent all the subtle shades of meaning in the real world. More about this in Chapter 5, but for now, begin to get into the thought process of realizing we have to choose good names for classes. Any questions? Okay. So we've talked about objects, and we've talked about classes. Let's talk about variables. There are a number of different kinds of variables. From the earliest days of programming, there were local variables inside procedures, methods, etc. Local variables. You know what they are. There are, in some programming languages, global variables. A variable which is outside of any procedure, any class, sits on its own, and it's accessible from everywhere. Okay? We don't use global variables in Java, but we do have local variables. And then inside classes, we can define two kinds of variables. The one kind is instance variables. And the other kind is class variables, also called static variables, with a static keyword. I want to distinguish between those two, and we're going to learn the lesson that you should avoid static variables, class variables with a passion, and stick to instance variables wherever you can. Okay? So, what is an instance variable? It's a variable defined inside a class that corresponds to a piece of data present in each instance. So every instance of student is going to have a student number, a separate student number. Each instance of student is going to have the student's name, etc., etc. In fact, we can break down our instance variables into two kinds, attributes and associations. I'm going to just mention this now. We're going to primarily leave this concept and come back to it in Chapter 5. Some of the instance variables are representing simple data, like people's names, a simple string. Date of birth, a simple date. Maybe things that are integers, things that are floating point values. Typically, simple data that is declared as a type that is defined by your programming language. Okay? The other main kind of instance variable is used to represent what are called associations. These are relationships that you define from one class in your system to another. So the relationship between an employee and that employee's supervisor. Okay, they're both different people. One's an employee, one's a manager. You have a relationship. You have to store data about that relationship, stored in instance variables, and we call that kind of relationship an association. The course is taken by a student. It's a relationship between the class student that you create in your application and the class course section that you create in your application. and you have to work out a set of instance variables to deal with that relationship and manage it. Associations are more complex. We're going to learn in detail how to work with them in Chapter 5. Attributes are simple, and we'll mostly focus on those at the start. Any questions about what an instance variable is? Okay. Let us make the important distinction between a variable and an object. Okay, a variable is a placeholder. It is a place where you put an object. In fact, we say that a variable refers to an object. You can have an object sitting here, and the variable, a placeholder, has some kind of a pointer or reference to that object. There might be another variable over here that has a pointer or reference to that same object. The object is the chunk of memory. Variable, whether it be an instance variable or a local variable, or some other kind of variable, is a place in which you put pointers or references to objects. Now, in some variables you can put primitive data, which are things like integers and characters. But we'll leave those aside for now. Just think in terms of objects. An object, chunk of memory, variables refer or point to that. I'm primarily going to be talking in the Java context. The C++ context is much, much more complex, because in C++ you can actually have these chunks of memory right inside the variable permanently, inside the variable, rather than having these references. But in Java, we're dealing with references, okay? And an object can be referred to by several different variables at the same time. It's quite common that you have an instance variable that has a reference to some object, and a local variable manipulating some algorithm picks that up and does some work with it and has a reference to the same object. Okay, that can happen quite readily. Now, we said that an object has a class. A variable has a type. The type determines what kinds of objects can be put in that variable. So, for example, and let's just use a sort of visual metaphor for a second. If I have a variable that's square, I can only put a square object in it. If I have a variable that's circular, I can only put a circular object in it. So I have variables of square type and variables of circle type. Okay, imagine a little children's toy where you have these little sticks and little shaped holes, and the kid has to learn which kind of sticks can be hammered into which kind of holes. Basically, that's the concept. Okay? It's more complex when we have polymorphism and inheritance, which we'll get to in a while. But in general, a variable has a type, and you can only put objects in a variable that have that have a class that corresponds to the type of the variable. Any questions? In Java, you definitely are going to be specifying the types of variables. There are programming languages like Smalltalk, which are much looser. But still, even in those programming languages, such as Smalltalk, where there's basically one grand type for all variables, there still is the concept of type. It's just that there's one type. And all object can be put in any variable in Smalltalk. But in Java and C++, typing is said to be strong. And we have strong restrictions over what variables can contain what objects. Now, I mentioned or alluded to the fact a few minutes ago that in addition to instance variables, we've also got these things called either static or class variables. Static and class is synonymous in this context. A class variable is the same thing as a static variable. In the old days, we talked about class variables, which basically means that a variable is shared by all instances of the class. Instance variable, a variable is only accessible by the one instance. That's the difference. Instance variable, one instance. Class variable, the value is accessible by all instances. When C++ came along, they used the keyword static to tag class variables. And in Java, they use the same keyword. And so sometimes people just use the word static variable. But it doesn't mean that the value can't be changed. Static is a bit confusing because people think static can't be changed. Yeah, maybe you don't want to change it. But it is still could be changed by certain methods. So the key is, if one instance sets the value of a class or static variable, then all the other instances see the same changed value. We want to use class variables very, very carefully and rarely. Typical uses which are valid are storing constants that we know will be unlikely to change, like the value of pi in a mathematical class, or lookup tables where we have a standard algorithm that is going to be doing some kind of computation, always using the same values. There are a number of other situations we'll see later on in the course. But unless it's one of these standard situations, the rule is don't use static variables. Use instance variables, because static variables lead to bad design. We'll learn more as the course goes on. Any comments? You will see plenty of bad design out there in industry where these are used. But don't let that lead you to think that you should use them too. Yeah?
An instance of a class can change the class variable.
An instance of a class can change the value that's stored in a class variable. Absolutely, yes.
What do you call the variable that cannot be changed?
Oh, well, that's a different thing. That's a different thing entirely. And depending on the programming language, I mean, the concept of constant is really the concept there. But in Java, we don't have that constant. In Java, we have the concept of final as well. I don't want to get into these levels of detail, though, because they're beyond the scope of this lecture. But I suggest that you go look up the Java reference or ask me, offline about that. But yes, static is not to be confused with constant and final. Those are totally different concepts. Okay, so we've talked a little bit about the kind of structural things that you're going to store in classes. Let's talk about the behavioral things. We're going to talk about methods versus operations. And we're going to start with the concept of operation. Okay? An operation is an abstraction of a set of methods. Let's just think about it as an abstraction with a name that does something, and you don't really care how it's going to be implemented as you start. When you're doing object-oriented analysis, high-level thinking, you don't think about the individual methods. You think about operations, and you say, this class or this set of classes is going to be able to do this particular operation, such as compute the area of a shape. So if I had a hierarchy, a class hierarchy of different kinds of shapes, squares, circles, rectangles, triangles, etc., the way I compute area will differ from class to class. Obviously, calculating area of a circle is not the same as calculating area of a rectangle. Different standard algorithms that you will have learned in your early schooling will be applied. But there's one abstract operation, compute area. Multiple methods for doing it. So a method is then a procedural abstraction, okay, used to implement the behavior in a class. It's going to have code. It's going to have an algorithm inside it. And the different classes will have methods with the same name to implement that abstract operation we talked about. Any questions? I'm sure you've all heard of methods. The term operation might be new. The key is to distinguish between them. And that moves us on to, on slide 15, polymorphism. Polymorphism is one of the powerful facilities in object-oriented systems. It is, along with inheritance, which we'll talk about in a minute, it is one of the key things that defines an object-oriented system. If you don't have polymorphism in a programming language, it cannot be called object-oriented. What it means, poly means many, morph means shape, so many shapes, i.e. many methods that implement an operation. So you have to have, in order to have polymorphism, you have to have multiple methods of the same name that do conceptually the same thing, just using different algorithms. The choice of which one to execute depends at runtime on which particular class of object is in a given variable. Now, if you don't have an inheritance hierarchy and you just have a single class on its own, you can't have polymorphism, because you can declare a variable of that class and you know that that variable is always going to have objects of that class in it. So polymorphism only kicks in when you actually have an inheritance hierarchy and you have a bunch of subclasses and you declare a variable as a superclass, and in those subclasses you don't know which of those subclasses is going to show up at runtime in a given variable. And so at runtime, the system has to look and see what class is in the variable and then choose the appropriate method to run at runtime. If it's a circle, run the circle algorithm, the circle version of calculate area. If it's a triangle, run the triangle version. And the benefit of polymorphism is that you don't have to write if circle do this, if triangle do this, if rectangle do that, or switch, case, rectangle, this, break, case, whatever, break. Okay? In other words, polymorphism simplifies coding by cutting out statements like if, then, else, and so on. It also allows you to add things easily and quickly without having to write extra code all over the place to show that you plug new things in. You can plug new classes into the hierarchy. As long as you define the methods that work according to what's defined in superclasses, your new class should work without any problems. Hopefully, at least. So the idea is polymorphism is supposed to simplify things. Now, it can be abused, and you can end up with complicated situations, but if you have a good understanding of polymorphism and the way it works, then you get a lot of power and you can program much faster. We're going to spend some considerable amount of time later on in this lecture and the early part of next lecture talking about the effects of polymorphism in the context of a particular class hierarchy. Any questions right away about polymorphism? Let us then talk a little bit about classes and inheritance hierarchies. First of all, we have a few pieces of terminology. The superclass. A superclass is a class which has subclasses. That's basically it. The superclass contains information that will be inherited, that will be found in all of the subclasses. Okay, now I think we have an example here. So account on slide 17 is a superclass, and it will define everything which is in common among all accounts, including the three subclasses: savings account, checking account, mortgage account. Okay, back to slide 16. The inheritance hierarchy is showing the relationships, the superclass-subclass relationships among a set of classes. The account hierarchy only has 2 levels of hierarchy, but we can have many levels, and we'll see a many-leveled example in a few minutes. The triangle is the key. Triangle points to a superclass. The apex of the triangle pointing up to the superclass. Now, if you create these diagrams using tools such as rational rows and many other tools that are out there, TogetherSoft, for example, look at the website, you'll see tools for drawing these diagrams, and some in the lab. You'll discover that you can draw these diagrams upside down. So you can, in fact, draw the savings account, checking account, mortgage account above, but then the triangle's also pointing down the subclass. My advice to you, don't do it. Always make the inheritance hierarchy so the superclass is on top and subclasses are below it. That way it's easier to understand and prevents confusion. But if you read diagrams, look for the direction of the arrow, it points to a superclass. Questions? And then we have the term inheritance. Inheritance, along with polymorphism, is one of the key contributions of the object-oriented paradigm. And the definition I'm showing here says it's the implicit possession, implicit is key, of by all subclasses of whatever is defined in superclasses. So, if I define instance variables in account, they will be present in savings account, checking account, mortgage account. They will be there. you can use them, you can program with them. If I define methods up here, they will be there down below. If I define static variables, they will also be there down below. Things inherit, okay? Right now we're just going to focus, however, on our instance variables and instance methods, because those are the ones that we're going to work with 99% of the time. You've got to remember that they do exist down below. There is a funny keyword in Java called private that confuses people sometimes, but even stuff that is declared as private inherits. Okay? The only difference is that you can't write new code in savings account to work with private variables, but private variables of account are still present in savings account. It's just that the only code that can work with those variables is code that was also inherited from account. So don't get confused about that issue. It's often a source of confusion. All instance methods, instance variables will definitely inherit. Now, how are we going to go about making sure that when we create class hierarchies that we do a good job? We have to check our work. And one of the key things is to make sure that when we create subclasses, that they follow what's called the ISA rule. The ISA rule says that you should be able to read a sentence, whatever subclass, ISA or ISAN, whatever superclass, and it should make sense in the context. So, a checking account is an account. ISA. It makes sense. Yes? Are all checking accounts accounts? Yes. So that's a valid generalization. You can make a subclass checking account. It's not violating the ISA rule. A village is a municipality. Is that valid? Yes. Sure. All villages are municipalities. So that makes sense. What about a province as a subclass of country? Does that make sense? Can you say a province is a country? Not in general. And there may be certain separatists who would, want to do that, but in the object-oriented context, you can't say that, because you have to apply always. You can't always say a province is a country. So that's an invalid generalization. They may be both subclasses of some common superclass, like political territory, but you can't put a province as a subclass of country. However, a lot of people will make the mistake and do this. And why will they do this? Because they get confused, they make the mistake and they think, oh, well, province is small, country is big, therefore province must be a subclass of the bigger thing. Nothing to do with small and big, it's nothing to do with parts and wholes, it's to do with the ISA relationship. One thing is a special kind of the superclass. Those are the only circumstances in which you're allowed to make subclasses of a superclass. Questions? Now, having the ISA rule apply isn't necessarily, doesn't guarantee that you're doing good design, but it guarantees you're doing bad design if you violate it. So, it's the first rule that we should think about. Every time you create a subclass, you should check mentally, does it follow the ISA rule with the superclass? You will definitely lose marks if you don't violate the ISA. It's one of the fundamental core concepts in this course that everybody should get 100% on by the time you're done. Okay? On slide 19, we see a much larger inheritance hierarchy. We start off with a grand superclass mathematical object. It breaks down into shape, point, and matrix, 3 different kinds of mathematical object. We can ask ourselves, is a shape a mathematical object? Seems to make sense. Is a point a mathematical object? Yeah. Is a matrix a mathematical object? Yeah, seems to make sense. And then we can go down one step further beyond that to break down shape into subclasses. A 2-dimensional shape, 3-dimensional shape. I call them shape 2D, shape 3D, because I think these are shorter, simpler names that are just as easy to understand. And then shape 2D breaks down into ellipse, of which a circle is a special kind, and polygon, which quadrilateral is a special kind, and then a rectangle is a kind of quadrilateral. So I get down to 6 levels of depth here at the bottom. And each level of depth I can add extra information. So all shapes have certain properties, all two-dimensional shapes have certain additional properties, all polygons have certain properties beyond that, all quadrilaterals have four corners, 4 edges, all rectangles have those edges all lined up vertically and horizontally. So I'm adding additional information as I go down, but everything that applied up above will apply to things found below in the hierarchy. That's inheritance. Any questions? Now, I was expecting somebody might ask the question, well, what about circle and ellipse? Is a circle a kind of ellipse? And mathematically, the answer is yes. It is a constrained ellipse. An ellipse in general, you know what an ellipse looks like, and it has 2 foci, and it also has a major and a minor axis. Well, a circle also has those, except that the 2 foci are on top of each other. We just call it the center. And the major and the minor axis are equal to each other as well. So we can still say that a circle is a special kind of ellipse. We will see in a few slides' time that this might not be the optimal solution. We're going to take a look at this whole shape hierarchy here, and we're going to see that there might be other approaches. I would appreciate if the person who's beeping could stop the beeping permanently, okay? Thank you very much. The circle and ellipse maybe could be organized in a slightly different structure, okay? We'll see that in a little while. So, one of the things we have to do when we're creating hierarchies is to check the is a rule. Another thing we have to do is to make sure that inheritance makes sense for everything which we're going to put in the superclasses. Make sure that, for example, all of these things make sense in all of the subclasses. So, we have a count, and it has a balance. Do all of the savings account, checking account, mortgage account have a balance? Sure. Right, so that one is valid. Opened. Gee, that's badly named. It should be open date. Okay? We could fix that. Put there as an example, show you something that could be fixed. So, the account open date, does that apply to all the other kinds of accounts? Yeah. So it makes sense that all of the other accounts, when you create an objective savings account, it has a balance, it has an open date. What about credit or overdraft limit? This is the amount of money that you can go in the red, maximum. Does that make sense for all 3 kinds of accounts? Well, it makes sense for a mortgage. Generally speaking, you owe money on a mortgage. In fact, you're almost always in the red. Pretty strange to have a mortgage where you're not in the red. Checking account, you call it an overdraft limit. You may be 0, but a lot of people have overdraft limits on their checking account. Big interest if you have it, but hey, the bank makes money that way. Savings accounts, do they have overdraft limits? Depends, right? You could imagine a bank that doesn't allow overdrafts ever on their savings accounts. So you might argue that we shouldn't allow credit or overdraft limit to inherit into savings account, because we might say, the bank might say, savings accounts, by definition, do not allow overdraft. They're for saving money in, damn it. You're not borrowing money from a savings account, making it a negative balance. So you might say, well, okay, we won't put a credit and overdraft limit up in account because we don't want it to inherit into savings account, and we'll put it in checking account and in mortgage account because it applies in both of these 2. And leave it out of account so it doesn't inherit to savings account. What would be the problem of putting credit or overdraft limit in checking account and mortgage account? Any thoughts of why or how that could be a problem? Yeah?
It should actually be split so that the credit in the checking account would be the overdraft under the mortgage credit.
Okay, his suggestion was that in a checking account it should be called overdraft limit, and in the mortgage account it could be called credit limit. Okay, now that's one possibility. The problem with that is that conceptually it amounts to the same thing. Any algorithm that's going to do calculations on accounts, it would be kind of nice if we could just say when somebody tries to increase their debt look at the same variable rather than say, well, if it's the checking account, look at this variable. If it's a mortgage account, look at that variable. So it makes sense to have, because it's the same concept, to use the same variable. That wasn't the issue I was getting at. It was a very good observation, but there is another issue. Yeah?
You can put another class between the checking account, mortgage account, and the...
Okay, his suggestion was to put another account that is a superclass of checking and mortgage account, but is a subclass of account, and which has creditor overdraft limit in it. And I agree that that is a decent way. If you insist on not putting it in account because you don't want it in savings account, you can put a class intermediate between the two. And that is a standard way of modifying class hierarchies. It's what's called a refactoring technique, and we might choose to do that. And the reason why we might choose to do that is because we don't want to have redundant, we don't want to have the thing defined in checking account and defined in mortgage account. Because then we're not going to take advantage of reuse. We're going to have code in checking account that does the work with this value, and code in mortgage account that does work with this value. What we'd like is all the code that applies to creditor overdraft limit to be put in some common superclass. In this case, it would be account, or in his suggestion, it would be the intermediate class that does that. Yeah?
You also have to bring the calculator interest down, probably because...
Ah, oh, that would be a ramification. Sure, exactly. Often when you make changes, you have to think about moving other things around. Exactly. Personally, I would like to keep it up here. Even if my bank came along and said to me, sorry, savings accounts never have a negative balance, I would put it up in account anyway. And the reason why is because it makes your system more flexible. For starters, you wouldn't have to put that intermediate class. And secondly, you could just have a rule that said this value never becomes negative, it's always 0. But it allows for flexibility. If in 5 years' time the bank comes along and says, for a certain class of customers, we're going to allow them to have temporary negative balances in their savings account. Oh boy, you've got to change your system big time. Whereas if we just put it up here and allowed for the possibility of, of eventual changing the rule and letting it be non-zero, changes are less. So, yeah, last time we talked about maintainability, designing systems to make them easier to change. So keeping the credit and overdraft limit up here builds maintainability into our system. Questions? Okay. Now, this is a big slide we're going to spend a lot of time on, slide 21. This is a expanded, much more detailed hierarchy of two-dimensional shapes. It's part of the hierarchy we saw a few minutes ago, where we took off the other mathematical objects and the three-dimensional shapes. It's just two-dimensional shapes. And what I've done is I've added in my details of all of the instance variables, like center, and all of my operations, like translate, get center, etc. We're going to study this in detail for a few minutes. First of all, let's start at the top of the hierarchy. I see shape 2D, and I see that it has an instance variable called center. What this is saying is it's saying the only thing that we can say about a two-dimensional shape in general is that it has a center. Everything else, such as things that are found in rectangles like height and width, are only defined further down in the hierarchy. So, can I create an instance of shape 2D? Can I create an instance of two-dimensional shape? Just say new shape 2D. Give it the center. Does that make sense? See some nodding of heads. How many people think I can do that? Well, I should be able to do that. Okay, a few people. How many people think I shouldn't be able to do that? A few people. Why not? What is wrong with being able to say, yeah, I can create arbitrary shape 2D by just saying new shape 2D? What's wrong with that? Any thoughts? No? Nobody? People think it's probably not doable, but no real reason? Yeah?
Well, if you have get area, you probably won't be able to get an area if you don't have the same.
that is a good answer. He said that if I want to get the area, I won't be able to get the area if I only have the center. I can't do anything, in fact, with an instance of class shape 2D, because I can't draw a picture of it. I can't calculate its area. I can't, calculate its perimeter, its bounding rectangle. I can't rotate it. But it doesn't make much sense to rotate it if I only have the center. I can't do anything serious with it because I don't have the information defined. In order to have a real object that is useful in my system, I have to actually say, well, it's a circle with a information about its radius, or it's an ellipse with information about its major and minor axes, or it's a rectangle with its height and width. Okay, so at the bottom of the hierarchy here, we have enough information to be able to display these things on the screen and calculate things about them. Higher up in the hierarchy, we don't. So shape 2D is going to be what is called an abstract class. And in fact, we're going to declare in Java, when we declare this class, we're going to declare it with the keyword abstract. What that means is, it doesn't make sense to create instances of this. We only can create instances of some subclass of that where all the information is properly defined and all the computations can be actually done. The only purpose of having the abstract class, I guess there's two purposes really. One is, it allows us to declare variables in which we can then put any of the lower level classes. So we can declare a variable of type shape 2D, which we can put objects, up there are circles, ellipses, rectangles, regular polygons, arbitrary polygons. That's the first thing. The second thing is it allows us to gather together those things which will be in common among all of the subclasses. So everything's going to have a center, so we can put that there. And everything can be translated. That means moved. The center can be moved, shifted in some direction. And we can also get the center. We have concrete code for those things. Notice, by the way, the difference between what's written in italics and what is not written in italics here. Center is not in italics. That means that we're going to have a real variable there. Translate and get center are not in italics. That means we're going to have real methods there. However, rotate, change scale, get area, etc. are in italics. That means that they are going to be abstract. It means that we are defining that operations with these names will exist, and in fact we're going to just say in Java abstract and not give any body of code for these things. What it means to say abstract method rotate or abstract operation rotate is that somewhere down below there has to be a concrete implementation of a rotate method. Maybe more than one. And there has to be one in each path from shape 2D down to the bottom. Okay, so let's take a look for them. Rotate. Going down, do I see it in elliptical shape? No. So that means it must be in circle and ellipse, because circle and ellipse are my bottom of my hierarchy. It's got to be found by the time I get down there. So I see one in circle, and I see one in ellipse. Going down the polygon path, I see one in simple polygon, rotate. So I have a concrete method there in simple polygon. And that means that's good enough. I don't have to have one at the very bottom because this one in simple polygon will inherit to the bottom. And there has to also be one in arbitrary polygon. And there is. There it is. So if I declare something abstract by showing it in italics in this diagram, that means that I must declare a concrete version where there's a real method to do that by the time I get to the bottom of the hierarchy. It doesn't have to be at the bottom. By the time I get to the bottom going down, in each branch, I have to have concrete implementation of that. And that means that I've enabled polymorphism to take place. I can declare a variable of type shape 2D, and I can then put some concrete object, a circle, ellipse, a rectangle, a regular polygon, or an arbitrary polygon in it, and I can call the method. I can call the operation, sorry, rotate, and the system will figure out which of these concrete methods in circle, ellipse, simple polygon, or arbitrary polygon to call. Okay, if it's a rectangle or regular polygon, it'll use the one from simple polygon. If it's a circle, it'll use the one from circle, etc., etc. So that's the principle. And you have to be able to look at a class hierarchy like this and have a thorough understanding of what the effect is by looking at what's abstract and what's not. And you have to be able to design these hierarchies, putting appropriate things that make sense everywhere in the appropriate superclass. Label them abstract if they need concrete implementations below, but if they make sense abstractly, they should be labeled as abstract in a superclass. Any questions before we go on? Okay, let's take a look at a few little interesting... Oh, question, yeah.
Where would you define those methods in italics? In the lowest level, or...?
No, it could be anywhere below. In this case, in rotate, it's not at the lowest level, right? In rotate, it's in simple polygon, not in rectangle or regular polygon. Just has to be somewhere, but before I get to the concrete classes, that's all that matters. Okay, so let's just review the terminology. Abstract classes, by the way, are shown in italics, so this shape 2D is written in italics. We also have elliptical shape as an abstract class, polygon is an abstract class, simple polygon is an abstract class, and then the ones which are not in italics are concrete. We can create real instances of these. And then we have abstract methods that are in italics and concrete methods. All the methods in shape 2D will inherit, so for example, translate will inherit the real method, whereas rotate is just the abstract operation inherits, and you have to look down to find the concrete implementation. Let's take a look at a couple of other interesting situations in this diagram. Notice we have circle and ellipse next door to each other. Earlier on, in the previous slide, I showed circle as a subclass of ellipse. Here I'm showing them both as subclasses of elliptical shape. The reason why I did that is in order to simplify the overall design of the classes as a whole. There are a number of things that are true in ellipses, like being able to change the semi-major axis and semi-minor axis, that I just didn't want to be able to say for all circles. So even though mathematically a circle is a subclass of ellipse, I don't want to be able to fiddle with the major axis of a circle, or the minor axis of a circle. I want to just be able to change the radius. Okay? So the ellipse has more methods, and some methods that don't logically apply to circles. And that's why I went from the analytical stage of just drawing a hierarchy and following the pure is a rule, to a more implementation-oriented setup where I decided that things like get focus 1, get focus 2, although they would abstractly, logically make sense in a circle, it just confuses people using circle. I just prefer to have, get center. And for the radius, get radius, a single get radius in circle instead of get semi-major axis, get semi-minor axis, which is the two things which are different in an ellipse. Okay, another observation. Let's take a look at the method and operation get bounding rectangle. Okay, there is an operation get bounding rectangle that is defined at the top of the hierarchy, so it makes sense everywhere. We talk about it, we can call get bounding rectangle of any two-dimensional shape. Fine. What is a get bounding rectangle? Basically, it's a rectangle that can be drawn, the smallest rectangle that will fit around a shape. So for example, if I have a circle, okay, the bounding rectangle is the thing that goes around the circle. Okay, it's a thing that you can compute. You might find it useful in certain kinds of applications. Notice that in shape 2D, it's abstract. Okay, so where are the implementations of that? Well, going down. I see one in polygon. Fine. So in polygon, I can compute the bounding rectangle. How come I can compute the bounding rectangle in polygon? Because there's no new information. I only have a center. So anybody think, how can I do that? Well, the answer is that I can call the get vertices method. And the get vertices method will give me enough information to be able to compute the bounding rectangle. But then you say, but get vertices is abstract. Well, fine. At runtime, all I'm ever going to have is a rectangle or a regular polygon or an arbitrary polygon. I'm only going to have these concrete classes. Right? So I'm guaranteed that I'm going to have one of these things, and I'm going to be able to calculate the real get vertices method down here, or down here, or down here. I'm going to be able to do that calculation. And because I know I can do that, the get bounding rectangle, I can have a concrete get bounding rectangle method at any level higher up, because I know I can call get vertices. Because there will be at runtime an actual version to run. So even though I haven't introduced any new attributes, any new anything beyond center and polygon, I can have a concrete method at this level. So you can see lots of little subtleties with the interaction between polymorphism and inheritance. And one of the skills that you're going to need to pick up quite early in this course is an ability to look at these diagrams and understand what method will be called under what circumstance. Okay? And later on to be able to design hierarchies that have appropriate methods at appropriate levels and use appropriate use of abstract classes or abstract methods. Yeah?
What would you put the square in all this
Hierarchy.
Yeah.
His question is, where would we put the class square in this hierarchy? Can anybody give me an answer to that question? Yep. The suggestion was it should be a subclass of rectangle, and if we have a class square, that would be where it would be. Or, what's the other possibilities? Yeah? Okay, could be now, here's an interesting thing. Notice an analogy here. We've got circle and ellipse. Ellipse is a bit like a twisted rectangle, and a circle is a bit like a curved square, right? So you've got the same analogy. So what you could do is you could turn this thing into rectangular shape and have two subclasses, rectangle and square. Okay, that's one way of doing it. The other way is to put it as a subclass of a rectangle. If I put it as a subclass of rectangle, then a square's got a height and a width, which could be a problem because I could change the height without changing the width. So I have to make sure my code that changes the height changes the width at the same time so they're always equal. Or there's a third possibility. So one possibility, subclass of rectangle. Another possibility, a little threesome sub-hierarchy. Third possibility is do nothing. Don't create a square class. That it would be a legitimate design decision. Why would it be legitimate? Well, the answer is I could just make do with rectangles and just keep the width and height the same. The algorithms all work the same with rectangles and squares. With circles, there's much simpler algorithms for computing area of a circle than computing area of an ellipse. So I really do want to have a separate get area algorithm up here and a separate get perimeter length algorithm for a circle, because I really do need to do this split. But for a rectangle, gee, the computation savings of having a separate class is not much, so the only benefit would be to make sure that if it's a square, it stays a square, and it doesn't change into anything else accidentally. So maybe I decide that I'm going to trade off and not have a square class here to keep things a bit simpler. And maybe it makes some other code a wee bit more complex, but overall, it makes things simpler. So the last point I want to make today is, there's lots of design decisions and design alternatives that you have to think about. And this is just a classic case of thinking about design, thinking about alternatives, working out which is going to give us the highest quality in terms of maintainability, simplicity, reusability. Reusability in terms of what inherits, maintainability in terms of how easy it is to change. Okay? We'll continue on, leading on from this example next time.